Okay, looks like this is getting started. So let's go ahead and get started. Yeah, it would be good if we could move out of this room, because it is a little distracting to have everyone drinking their coffee over there. But we'll survive. We'll soldier on. And I'll try and speak loudly. Okay, so let me just remind you of what we were discussing last class. So we asked the following question. Here, let me... So we asked the following question. Does every mechanical system obey a minimization principle? Or, in other words, does the path that a system takes through configuration space extremize some function or some functional that will be a functional of the path through configuration space. And the claim, which I demonstrated last time, is that the answer is yes. And that if you have a system which starts out at some initial position, Q initial, so Q initial, which is the position or the state of the system at some time t initial, and the final state of the system is described by Q final, which is the value of the dynamical variables at some time t final, then the action, which is minimized, is the integral dt of the Lagrangian as a function of that path. So, in particular, we showed that a functional I, which is a function of another function, defined as follows. So if I define my functional I as some function y as the integral dx of some function of y, y prime, and x, then we showed that this functional is minimized, or rather extremized, I should say, because we only computed the first functional derivative, if the following quantity vanishes. So this quantity is known as the functional derivative of the functional I with respect to the function y, and it is given by the derivative of f with respect to y minus d by dx of the derivative of f with respect to y prime. Success?
No.
It's tough. Nothing. Okay, well, I'll just have to speak loudly. Are you guys particularly bothered by the voices in your head? No. Okay. That's good. So, yes. So, in particular, if we have a functional which depends on some function y, then that functional is extremized only if this functional derivative vanishes. And at the end, I described how if we have a functional of several functions, which I could call yi, or I as some index, then all I do here is I put some I indices in the appropriate place. And I see that this functional now will be minimized if a set of n differential equations are obeyed, namely that the n functional derivatives of I with respect to the yi vanish. So now all we need to do is compare this equation here to the equations of motion of a mechanical system. So what we conclude is that for a mechanical system, with Lagrangian L, that is a function of the QI dots and time, then the condition that the action, which is the integral of the Lagrangian, is extremized is just found by taking that previous equation, and everywhere I wrote I replaced that with S. Everywhere I wrote Q, I replaced that with Y. Everywhere I wrote X, I replaced that with T. And in particular, what we see is that the action is extremized only if the following differential equations vanish. So in particular, the functional derivative of the action with respect to the degrees of freedom has to vanish. So that's dl by dqi minus d by dt dl by dq dot. And these are the equations of motion of the mechanical system. In particular, these are the Euler-Lagrange equations. So, previously, last week, our discussion of the Lagrangian had primarily stressed the practical advantages of the Lagrangian approach. In particular, we saw that it was an extremely efficient way of writing down equations of motion. But we now see that it is, in addition, a conceptually new way of thinking about mechanics, where every mechanics problem, at least every mechanics problem for which there is a Lagrangian formulation, can be thought of as a minimization problem, in the same way that light travels along lines which are extrema of the length as a function of the curves that connect 2 points. Are there any questions on this before I continue? The calculus of variations, as I presented it last time, is, I'm sure, a little unfamiliar to you. So it may be useful for you to practice that derivation a little bit. And indeed, the problem set that I will hand out next Tuesday will give you plenty of opportunities to understand better the calculus of variations. But at least, I hope conceptually, the idea is clear. So any questions on that? Comments? Thoughts? Any emotions that this brings up in you that you would like to share with us? Okay. Yes. Emotions?
Not really related to classical mechanics, but when you say light extremizes distance,
yes.
How does that work with refraction? The shorter path.
Yes. The thing that is actually extremized is something slightly different in the presence of a refractive object. It's something that is essentially the amount of time it takes. So there is a version of the action that one can write down for light rays in the presence of refraction, which will reproduce all of the usual laws of optics. So in your in your sort of elementary optics class, you probably did not see that, but if you take more advanced optics, you will see that, I think. Yes, good question. And indeed, just about every system you have ever encountered has an action formulation. The only exceptions being dissipative systems or non-holonomic systems. But for example, electromagnetism has an action formulation. Most of the theories that you have heard about but not yet learned about have action formulations. And indeed, in your future lives as physicists, when people present to you the formulation of some theory of physics, the typical way that they will present it to you is by writing down an action. They will tell you what the degrees of freedom are, they will tell you what the action is, and then that completely specifies the theory. This is how electromagnetism can be defined. This is how general relativity can be defined. This is how all of the theories of particle physics can be defined. This is how most of the effective theories of condensed matter physics can be defined. This is how hydrodynamics, if one is studying astrophysics, can be defined. This is how magnetohydrodynamics can be defined, and so on and so forth. Not every theory, but many theories. So, although we have presented Lagrangians and actions in a relatively simple setting, primarily thinking about blocks sliding down planes and so forth, this is the conceptual formulation of theories of physics that will follow you for the rest of your lives as physicists, most likely. Any other questions? Okay. So let me work out a simple example for you. And in particular, I will work out an example that you already know. In particular, I will prove to you that the shortest distance between 2 points is a straight line. And I will prove it to you in 2 different ways, one easy and one slightly less easy. So in this case, the functional that we wish to minimize is a function of the curve that connects 2 points. So let's say that I have 2 points on a blackboard or a plane, and they are connected by some curve, which is parameterized by 2 functions, x of s and y of s. X and y are the Cartesian coordinates on the plane, and s is a parameter which labels different points along the curve. And then we seek the path which minimizes the length along the curve. And as you remember from your multivariable calculus class, that length is found by integrating an arc length, which is given by the Pythagorean formula, the integral of x dot squared plus y dot squared, where dot is d by ds. So this is the length of the curve, and it is the quantity which we wish to minimize. So we have 2 equations which must be satisfied, which are the functional derivatives of the length with respect to x and y. This would be a case where we have a functional that is a function of 2 functions, x of s and y of s. The functional derivative of L with respect to x of s is, well, there's the derivative of L with respect to x, which is 0, because L depends on x dot and not on x. And then there is the derivative with respect to s of the derivative of L with respect to x dot. And the derivative of L with respect to x dot is x dot divided by the square root of x dot squared plus y dot squared. There is a 1/2 that appears from taking the derivative of the square root, which is canceled by a 2 from the derivative of x dot squared. And if we write that out explicitly, so let's forget about, there's some overall minus sign. So when we take the derivative with respect to s, we get 2 terms. So there is a minus x double dot over the square root of x dot squared plus y dot squared, taking the derivative of the numerator, and then we must take the derivative of the denominator. So we have a factor of 2, a 1/2 x dot squared plus y dot squared to the 3/2. Sorry, I guess there's a minus sign because it's x dot squared plus y dot squared to the minus 1/2 power, and then twice the derivative of x dot squared. So we have an x dot squared times x double dot, because there's also 1 power of x dot from the numerator. And that is equal to 0. So multiplying multiplying that entire equation by x dot squared plus y dot squared to the 3/2 power, we can write this in a somewhat simpler form. So we have x dot squared x double dot minus x double dot. Oh, I'm sorry. You guys should have corrected me because I made a mistake here. Yeah, there's also, so there's x dot times the derivative of x dot squared plus y dot squared with respect to t, which is x dot x double dot plus y dot y double dot. Sorry, this is what happens when I don't look at my notes, and I give a lecture immediately after lunch. Yes, is that clear? Sorry about that. So what do we get? The equation of motion is x double dot times x dot squared plus y dot squared minus x dot times x dot x double dot plus y dot y double dot equals 0. Did I make any more mistakes? Speak now, forever hold your peace. Okay, so there's a bit of a cancellation, and we see that this is just x double dot y dot squared minus x dot y double dot. And the variational derivative of L with respect to y vanishing will give you the exact same equation except with x and y switched. So we will get y double dot x dot squared minus x dot y double dot. So these two equations at first sight look a little complicated, but in fact, if you stare at them for a second, you can see that this first equation can be written as x double dot over x dot is equal to y double dot over y dot. And so can the second equation. Did I make a mistake? Oh, I'm sorry. Thank you. Yes. Sorry about that. We would never make any progress without you guys helping me. Okay, so x double dot over x dot is y double dot over y dot. So this equation is the same as the statement that d by ds of log x dot is equal to d by ds of log y dot, or otherwise known as the statement that d by ds of log x dot over y dot is equal to 0, namely that x dot over y dot is equal to a constant. So remember here that we are thinking of x as a function of s. X dot is dx by ds. Y dot is dy by ds. So if you think of x as a function of y, then this is just the statement that dx by dy is equal to a constant. So this is just a statement that we have a straight line with constant slope. So, any questions on that? So that was the hard way of showing that the shortest distance between 2 points is a straight line. There's an easier way of showing it. So in order to understand what this easier way is, let's look at this action at the top of the page. So this action depends on x dot and y dot, but not on x and y. That means that if I define the momentum conjugate to x and the momentum conjugate to y, then those quantities will be constant. That's just the conservation of momentum that we discussed last class. And indeed, if you look at this equation here, this just says that d by ds of x dot over y dot squared plus the square root of x dot squared plus y dot squared is a constant. And that is, in fact, what we would have called d by ds of the momentum conjugate to x. Right? So remember that the momentum conjugate to x is the derivative of the Lagrangian, which in this case is the square root of x dot squared plus y dot squared, with respect to x dot, which is x dot over the square root of x dot squared plus y dot squared. And because the Lagrangian is independent of x, this is a constant. And likewise, the momentum conjugate to y is a constant. And in particular, that implies that their ratio, px over py, is x dot over y dot is constant. So whereas we could have gone ahead and worked out the equations of motion in detail, in fact, it is easier just to use a conservation rule that, in this case, is momentum conservation, which automatically, in sort of a one-line argument, will tell you that the shortest distance between 2 points is given by a straight line. Any questions? Okay, good. So I would like to make one further point. So I would like to note that the Lagrangian principle and the action principle that we have developed here is useful, but there is a slightly different way of using it involving what is known as Lagrange multipliers. Which in many cases is sort of technically much simpler to use. So you probably saw Lagrange multipliers in your multivariable calculus class. You may not remember what they are. It's one of those things that tends to be covered in a less than optimal manner. So I will just remind you what they are. So let me just remind you that our recipe so far requires writing the positions of the various parts of some system as a function of the dynamical variables, as well as possibly time. And in general, this may be quite complicated. So in order to write the action as a function of the QIs and their derivatives, that may be technically difficult to do. And so what I ask is whether there is a formulation of the action principle directly in terms of the R alphas. So in particular, so far our point of view has been that we write the degrees of freedom write the positions in terms of the degrees of freedom, and then we think about the action as a function of the degrees of freedom. And so we impose the constraints before writing down the action. Uh-oh. Can you see it now? Okay, there we go. But now what we would like to ask is there a way of imposing the constraints directly at the level of the equations of motion, rather than at the level of the action. In particular, could we write down a set of equations of motion treating the R alphas as some independent variables, and then only at the level of the equations of motion impose the fact that they are constrained in some way? And the answer is yes, and this involves what are known as Lagrange multipliers. So let's just remember what Lagrange multipliers are. So let's say I am presented with the following problem. So if I want to minimize some function, say of two variables, then the way that I do that is I take the derivative of the function with respect to x and the derivative with respect to y, and I set them both equal to 0. Okay, that's easy enough. But now, what if I am presented with a slightly more difficult problem? What if I want to minimize the function f subject to a constraint, say that some other function of x and y is equal to 0? So if I have a constrained minimization problem, where I would like to minimize the function subject to some other condition, then we do this using what are known as Lagrange multipliers. So what we do is we first note that if f is minimized such that g is equal to 0, then that implies that if we take the linear combination f plus lambda g, then this will be minimized for all lambda. Right? Because if g is equal to 0, then f plus lambda g is just f. So I can then treat this linear combination as the quantity that I want to minimize. And I see that that I have to take the derivative of f with respect to x plus lambda times the derivative of g with respect and set it equal to 0. And I also must take the y derivatives and set them equal to 0. And finally, I must also impose the constraint. And so what we have then are three equations for three unknowns: x, y, and lambda. So just to summarize, if I wish to minimize f subject to a constraint, then I have two alternatives. The first thing I could do is I could invert the constraint and write, for example, y as a function of x, plug that into my expression for f, and write f as a function only of x, and then take the derivative of f with respect to x and set it to 0. But it could be that g is a very complicated function which has no explicit inverse. In which case, an alternate way to proceed is to write down three equations treating x and y as independent variables, but introducing an additional variable, lambda, which is known as the Lagrange multiplier. And then I have three equations for three unknowns, x, y, and lambda, rather than one equation for one unknown in the first way of doing the computation. And the point is that this logic works for the calculation of variation, the calculus of variations as well. So in particular, let's imagine that I have m functions yi that depend on x. So I here runs from 1 up to m. And I have a functional I, which depends on the yi's, which, as before, will just be some integral of something that I could call f. And if I want to minimize I, subject to some constraint, which again will be a functional of the yi's, then I do that by introducing a Lagrange multiplier. And just to make things a little more general, I could imagine that I have more than one constraint. So for example, I could have a bunch of constraints that I will label by an index k. So this would be, let's call it m minus n constraints. So k runs from 1 up to m minus n. So if I have m functions subject to m minus n constraints, then I have n degrees of freedom remaining. So one way to proceed is to write the yi's as a function of n degrees of freedom. And then explicitly write down the action, or the functional I, as a function of those n degrees of freedom, and then write down the usual Euler-Lagrange equations. But the other way to proceed, using Lagrange multipliers, is to note that the functional I, or that the following functional needs to be minimized. In particular, if we consider the integral dx of f, so that was just I here, and we add lambda of x times our constraint, then this must be minimized for all values of lambda. And in general, if I have a bunch of different constraints labeled by some index k, then I will have k Lagrange multipliers, and one for each constraint, and I must sum over lambda of x times g of x over all k's. Can you not see? Here. Let me raise that up for you a little bit. And then the equations of motion are just the usual variational equations, Euler-Lagrange equations, that come from minimizing this quantity. So this is minimized for all lambda. And so the equations of motion will then be the variational derivative of f of I with respect to yi plus the sum over k, lambda k, times the derivative of g with respect to yi. Where these formulas for the variational derivatives are exactly the ones that I wrote down before, and I must, in addition, impose the constraints that gk is equal to 0. So here we have a system of, the first line consists of m equations, because I runs from 1 up to m. The second line consists of m minus n equations. So we have 2m minus n equations. And how many unknowns do we have? Well, we have yi, so that's n unknowns. And the lambda k's are m minus n unknowns. So we have 2m minus n equations for 2m minus n unknowns. So perhaps I can give you an example of this these Lagrange multipliers at work. So let me just give you a very simple example. You will work out a more complicated example in your problem set, not the one due Monday, but the one due the following Monday. So let's take the very simple example of a pendulum. So if I have a pendulum of mass m, which is attached by a rod of fixed length L to some fixed origin, then it has a kinetic energy. So the way that we solved this problem previously, is there a question? Okay. The way that we solved this problem previously is we took as our degree of freedom theta, and we wrote the kinetic energy and the potential energy as functions of theta. So this first guy was 1/2 ml squared theta dot squared, and the second guy was minus mgl cosine theta. And then the Lagrangian was 1/2 ml squared theta dot squared plus mgl cosine theta. And so the equation of motion is, well, first we have d by dt of the derivative of the Lagrangian with respect to theta dot, which is ml squared theta double dot. And then we subtract from that the derivative of mgl cosine theta with respect to theta, so we get plus gl sine theta. And I factored out an overall m, because both terms are proportional to m. So, of course, there's a different way of doing the problem. So the other way of doing the problem, so this was the first way, which is the sort of standard way, where we solve for the constraints at the very beginning. The other way of doing the problem is to treat x and y as independent variables and subject them to the constraint that x squared plus y squared is equal to L squared. Or x squared plus y squared minus L squared is equal to 0. And this quantity is what I would have called G. So G is x squared plus y squared minus L squared, and the Lagrangian is equal to 1/2 m x dot squared plus y dot squared minus mg y. And then in order to solve the system, I just treat L plus lambda g as a Lagrangian, and I minimize it. I write down the equations of motion for x and y separately. So this is 1/2 m x dot squared plus y dot squared minus mgy plus lambda times x squared plus y squared minus L squared. And taking the variational derivatives of this guy, so the variational derivative with respect to x will give us m x double dot, that's the time derivative, of dl by dx dot plus 2 lambda x, or sorry, minus 2 lambda x is equal to 0. The y equation is my double dot. Then there's the term coming from the derivative of mgy with respect to y. So plus mg, and finally minus 2 lambda y is equal to 0. And finally, we must impose the constraint that x squared plus y squared is equal to L squared. And these are viewed as 3 equations for lambda, x, and y. So let's note that we can find a linear combination of those first 2 equations, which will get rid of lambda. That's just found by subtracting the first 2 equations. So that gives us x double dot, or taking the first equation, dividing by x, and subtracting the second equation divided by y to get rid of the lambda. So that gives us m x double dot over x is equal to m y double dot over y plus g over y. Right? That's just setting the first equation divided by x equal to the second equation over y. That's just solving for lambda. Sorry, and there's an overall m. Or if I wanted to rewrite that, x double dot times y plus y double dot times x, minus y double dot times x minus gx is equal to 0. And my claim is that this is identical to the equation of motion I wrote earlier in terms of theta. So if we would like to check that, let's just use the fact that x is equal to L times sine theta, y is minus L times cosine theta, so x dot is L cosine theta, y dot is L sine theta times theta dot, and x double dot is L times cosine theta, theta double dot, minus sine theta, theta dot squared. And likewise, y double dot is L times sine theta, theta double dot, plus cosine theta, theta dot squared. So if we take these guys, plug them into that equation, what do we get? So x double dot times y will give us one term proportional to sine squared theta, sine theta, cosine theta, theta double dot. And then another term times, let's see, did I get this right here? Yeah. So x double dot times y, oh yeah, so x double dot times y will give us a term that looks like L times theta double dot times cosine squared theta. Then there'll be another term coming, which is minus L theta dot squared sine theta cosine theta. Then the y double dot times x term will be minus L times theta double dot sine squared theta plus theta dot squared sine theta cosine theta. Sorry, minus theta dot squared sine theta cosine theta. If I got that right. Those sine thetas and cosine thetas are supposed to cancel. Oh, then and we get theta double dot is equal to gx, or G times L sine theta. And I factor out an overall L. So hopefully, if I've gotten all of my signs right, the method of Lagrange multipliers gave the same answer as the equation of motion for the pendulum that I wrote down above. So that was a little fast, not because this is unimportant, but just because it's a straightforward mechanical procedure that you will get much practice with on this week's and next week's problem set. So that concludes what I had intended to say about the calculus of variations, about action principles, and about Lagrange multipliers. Just to summarize, we have concluded that every mechanical system is equivalent to an action principle, and there are two ways of using this action principle for a constrained system. So one can either solve the constraints and write the action as a function of the degrees of freedom, or one can minimize the action subject to some constraints, in which case one has to use the method of Lagrange multipliers and introduce additional sort of degrees of freedom that you could associate with these Lagrange multipliers, and then solve for them at the level of the equations of motion. Are there any questions on that? In practice, almost all of the problems that we will describe in this class are more efficiently approached in the first way by simply solving for the constraints at the level of the action. There are some systems where it is easier to leave the system as unconstrained and only impose the constraints at the level of the equations of motion. Such systems tend to involve very complicated constraints with non-invertible functions, transcendental functions, and so forth, whose inverses are not particularly pleasant to write down. But for practical purposes, simply solving for the constraints at the level of the action tends to be much more efficient than solving for the constraints at the level of the equations of motion. That is not always true, however, and on your problem set, for example, I will ask you to find the path of minimum length on a curved surface rather than on a plane. And in that case, the answer is almost trivial to write down using the method of Lagrange multipliers. But trying to invert the equations and solve for them explicitly is very, very complicated. So I include that as a demonstration of the utility of this method. Are there any questions before I continue? No questions? Okay. So, as I promised in the very beginning of this class, the course is roughly divided half into formal, more conceptual issues, and half into more practical matters where we apply these conceptual developments to understand important mechanical systems. So we have now completed our discussion of some formal stuff, Lagrangians and actions, and for the next 2 to 3 weeks, what we will do is we will consider a variety of mechanical systems, starting with very simple mechanical systems and working into more complicated mechanical systems. And along the way, we will put to use many of the concepts that we have learned over the last 2 weeks: Lagrangians, actions, Hamiltonians, conserved quantities, momenta, and so forth. And so at this point in the course, we now switch gears a little bit, and rather than simply writing down efficient ways of thinking about the equations of motion, we will proceed to solve them, at least when we can. So are there any comments before we continue? Okay. So the first topic that I would like to study is the subject of oscillators. So this is a subject that you probably are a little bored of from your freshman mechanics classes. Our approach this time will be very different, and it will emphasize the material in a way which will hopefully provide you with some new intuition onto problems involving oscillators, and will also be the first of many examples where we put our Lagrangian techniques to profitable use. Okay. So, so far, all we have done is written down equations of motion. But what we would now like to do is to begin to solve them. So, of course, for a generic system, the equations of motion are quite complicated and will typically not have a simple analytic solution that you can write down in terms of elementary functions. But for some particularly simple systems, it is the case that one can solve the equations of motion explicitly. So let's just consider a general one-dimensional system. A system with one degree of freedom, Q, and a Lagrangian, which is a function of Q and Q dot. And for the time being, let us consider only those systems where the Lagrangian has no explicit time dependence. Then, an equilibrium solution is one where Q is equal to constant. And so I will call that constant Q naught. So this is just what you usually think of as an equilibrium solution. The system starts with some initial state configuration given by Q naught, and it stays in that configuration for all time. So, which is to say, Q is independent of time. So, under what circumstances will this system have an equilibrium solution? Sorry, independent, not independent of time. So under what circumstances will a mechanical system have an equilibrium solution? So the equations of motion will be the Euler-Lagrange equations. So dl by dq minus d by dt, dl by dq dot is equal to 0. This is some second order differential equation. And so, because it is a second order differential equation, solutions are described by two pieces of initial data. So solutions depend on two pieces of initial data, namely the initial position and the initial first derivative of the position of the system. So they depend on the initial data of Q and Q dot at some time t. So if we are looking for an equilibrium solution, we wish to look for a solution where Q is equal to Q naught at some initial time, and Q dot is equal to 0. And then this will remain a solution. So it will remain at rest only if Q double dot vanishes. So we imagine looking for solutions to the equations of motion, dl by dq minus d by dt, dl by dq dot. And we start with some initial solution, some initial values for q with q dot equal to 0. And then we ask if when we plug that into the equations of motion, q double dot is equal to 0. So what does that mean? Well, the Lagrangian is the difference of the kinetic and potential energies. So if we write down the Euler-Lagrange equations explicitly, then we have the first term, which is the derivative with respect to t of the derivative of the Lagrangian with respect to q dot. V is independent of q dot, so that is just the derivative of the kinetic energy with respect to q dot. Plus the two terms involving the derivative of t with respect to q and v with respect to q. So if we look at this at an initial point where we're setting q to be a constant and q dot equals 0, then this term here will be involve terms with q dot and q double dot. This term here will be proportional to something linear. This term will be proportional to q dot, and this term will be some function of q. So what we see is that in order for this to vanish at a point where q dot is equal to 0, we need to have the derivative of the potential at this point q naught equal to 0. The first term in the Euler-Lagrange equations involves derivatives, so it involves q dot, which will be equal to 0, as well as q double dot. The second term, dt by dq, will have terms proportional to q dot, because kinetic energies are always proportional to q dot. That's what they do for a living. That's why we call them kinetic energies. They have velocity-dependent terms. And then there is a term which is a function of q, which is the derivative of the potential, what we would call the force in the standard Newtonian mechanics. And then this vanishes when the derivative of the potential with respect to q vanishes. So physically, of course, this is something with which you are very familiar. If you have some potential, say that looks like this, so if this is v as a function of q, then the places where the derivative of v vanishes, so for this function I have drawn, there are 3 of them, are places which are equilibrium points. They are points which, if I start with my system sitting at an equilibrium point, it will stay there for all time. Now, as you can probably see by looking at this picture for the potential, there are 2 qualitatively different types of equilibrium points. In particular, there are those where we are at a local minimum of the potential and those where we are at a local maximum of the potential. And these are known as stable and unstable equilibria. Are there any questions before I continue? Yes.
Could the third term goes like this?
Yes. We would call those marginal equilibria. Yeah. In particular, if the potential is exactly flat, then you would call it marginal. That's a sort of highly special case. So in that case, you would say that it is a flat direction or a marginal equilibrium or something like that. But generically, you will have only a local minimum or local maximum. later in the course, we will consider not just one-dimensional systems, but n-dimensional systems around equilibria. We will give a more systematic classification of equilibrium points, including this sort of system. Any other questions? Okay. So, physically, around a stable equilibrium, a small perturbation around that equilibrium point will remain small. That's why we call it stable. Whereas a small perturbation around an unstable equilibrium will grow in time. And indeed, you can see physically, if you have a particle, a ball rolling down around on a hill of the shape that I have drawn here, if the ball is up at the top of the hill and you perturb it slightly, then it'll roll off to the bottom to one of the unstable equilibrium points. And so intuitively, that explains why we call these stable and unstable equilibria. So let's describe that a little more systematically. So consider a small perturbation. Around an equilibrium point. So earlier I was calling an equilibrium point a place where Q is equal to Q naught, but I will just choose my dynamical variable so that Q naught is equal to 0. So I note that the equations of motion are unchanged. The physics is unchanged if I choose some new form for my degrees of freedom. So I can always shift my degrees of freedom to set Q naught equal to 0. And so then what I would like to do is expand my equations of motion and expand the Lagrangian in a perturbation series around this equilibrium point. So I wish to expand the Lagrangian order by order in powers of Q. So the first term in the expansion will just be a constant, which is the value of the Lagrangian at the equilibrium point, Q equals Q naught, with Q dot set equal to 0. Then there will be terms linear in Q, so there'll be a term proportional to Q, a term proportional to Q dot. At one order higher, there would be terms quadratic in Q, of which there are 3. Sorry, that's a little messy. A term proportional to Q squared, a term proportional to Q times Q dot, and a term proportional to Q dot squared. And if I were very energetic, I could continue to write down higher and higher order terms in this expansion. Now, I would like to use the following fact. So how many of you have already looked at the problem set, which is due on Monday? You can be honest. It's okay. Okay, not so many of you. So in your problem set, you'll show that the equations of motion are unchanged if you add a total time derivative to the Lagrangian. So in your problem set, you will prove this explicitly, but it is almost obvious once you know about actions. So why is that? So let's imagine taking L to L plus a time derivative, d by dt, of J. And then we know that the equations of motion follow from minimizing an action. And if you add a total time derivative to L, then the action will pick up a term which is the integral dt of a total derivative of j, which is just by the fundamental theorem of calculus, j evaluated at t1 minus j evaluated at t2, t0. So in particular, it is independent of the choice of path through configuration space. So that means that minimizing the action with respect to the path will not change if I add a total derivative to the Lagrangian. So this argument that I have given you is a slick one. I will ask you to verify this directly by writing down Euler-Lagrange equations in the problem set, which is due Monday. But what it means is that if I consider my small perturbation around an equilibrium point at q equal to 0, then I can ignore all of the terms which are total time derivatives. So in particular, I can ignore the a term, because that's the derivative of a times t, the c term, which is the derivative of q, c times q, and the e term, which is the derivative of 1/2 e q squared. And moreover, I am looking for an equilibrium point, which means that the derivative of the potential with respect to q is equal to 0. So looking at this Lagrangian, you see that the potential is b times q plus d times q squared plus higher order terms. So looking for an equilibrium point where dv by dq is equal to 0 implies that b is equal to 0. So what that means is that the Lagrangian of the small perturbations around an equilibrium point at q equals 0 will take the form f times q dot squared plus d times q squared. Or I could write this as 2f times 1/2 q dot squared plus d over 2f times q squared. And another thing which I believe I asked you to show in the problem set is that the equations of motion are also unchanged if we multiply the Lagrangian by a constant. Does anyone who's looked at the problem set, can you verify that? Yes. So the Lagrangian is also unchanged if I multiply it by 1 over 2f. So the physics is unchanged if I multiply the Lagrangian by 1 over 2f. So that means that the equations of motion describing the small perturbations around an equilibrium are given by the action 1/2 q dot squared plus d over f times q squared. So, are there any questions before I continue? So what we have seen is that for an arbitrary equilibrium point, the behavior of the small fluctuations around that point are described by a single number, which is d over f. That number has a name, and the name of that number is the square of the frequency. So let us define the frequency of the perturbation. So that'll be a number I'll call omega. The omega squared is equal to minus d over f. So if d over f is negative, then omega will be a real number. And if d over f is positive, then omega will be an imaginary number. And so without any further ado, we can write down the equations of motion of the system. And what are the equations of motion? Well, we have the derivative of the Lagrangian. We have d by dt of the derivative of the Lagrangian with respect to q dot, which gives us q double dot. And then we subtract the derivative of the Lagrangian with respect to q. And set that equal to 0. Or, with our definition of omega squared, that is q double dot plus omega squared q is equal to 0. Even I can solve that differential equation. You probably remember this differential equation from your freshman physics classes or from many, many other classes. So what are the solutions to this differential equation? So if omega is real, which is to say d over f is negative, then the solutions are given by sines and cosines. So the most general solution to this differential equation will be q is equal to some number a times sine omega t plus b times cosine omega t. You can check that q dot of this, you get 1 power of omega, q double dot, you get another power of omega, and because the second derivative of sine is minus sine, the second derivative of cosine is minus cosine. Indeed, when d squared over f is negative and omega squared is positive, the solution to this equation of motion is a linear combination of sines and cosines. So in this case, the solutions just oscillate. Around q equals 0, and this oscillation has frequency omega. In particular, it takes a time 2 pi over omega to complete one oscillation. And in this case, the equilibrium point is stable. The reason why it's stable is that if you start out with some perturbation around the equilibrium point, the size in that perturbation remains constant in time. It just oscillates. On the other hand, if omega is imaginary, which is to say if d over f is positive, then the equations look like q double dot now minus a positive number, which is the absolute value of omega squared q, is equal to 0. And that is perhaps an even easier differential equation to solve than the previous one. The solutions are given by q is some constant times e to the plus omega t. Sorry, that's a plus, not a t. So that's, wow. Yeah, my pluses look exactly like t's. E to the plus the absolute value of omega t, plus another constant times e to the minus absolute value of omega times t. So the solutions are given by exponentials rather than by sines or cosines. Or you could write them as sinches and coches if you so desire. But the point is that generically, which is to say, unless we consider the very, very, very special initial conditions where a is equal to 0, then the perturbation grows in time. And this is therefore called an unstable equilibrium point. So I would like to emphasize something here. When you encountered oscillators in your freshman physics classes, you probably talked a lot about masses on springs. And masses on springs are fine. I have no problem with masses on springs. But the real reason why you studied oscillators is not because masses on springs are such an important topic that they were worth dedicating so much of your time and energy to, but rather because, as we have seen, everything is an oscillator. If you take any system around an equilibrium point, if that equilibrium point is stable, then it is described, at least in the limit where the fluctuations are small, by an oscillator. That is true not just of masses on springs described around the equilibrium point of the spring. It is also true of much more interesting systems, such as pendulums, which are small fluctuations around the place where the pendulum is at rest. It is also true of, for example, the quantum field describing the fluctuation of a particle around the vacuum of space-time. It is true for molecules, which are in small perturbation around their rest configurations. It is true for quantum mechanical systems, which are in small perturbation around their rest configurations. Anytime you have a stable configuration and you are studying these small perturbations around a stable configuration, it is an oscillator. And as we will see later on in this class, if you have a system of many degrees of freedom and you study it in equilibrium around a stable point, then it is given by n oscillators. Here we have just considered the simple example of one oscillator. So there's a reason why in your quantum mechanics class you spent all this time studying the simple harmonic oscillator, why you spent all this time learning about masses on springs and stuff like that in your freshman physics class. And the reason is that, as we have seen, everything is an oscillator if you look at it the right way. Any questions on that? So perhaps I can end just with a reminder, which is that this system with omega real is known as the simple harmonic oscillator. And that is to distinguish it from other sorts of oscillatory systems that we will start considering next time. Are there any questions before we leave for the day? Good. I'll see you on Tuesday.
What time do we need to end?